Welcome. My name is Maurice Pomerantz. I'm the Executive Director of the NYU Abu Dhabi Institute and a professor of classical Arabic literature here at NYU. The Institute, as you know, is a center of academic research, artistic creation, and public outreach. We host around 50 public lectures on a variety of topics throughout the year here in Abu Dhabi. And one of our missions at the Institute is to bring you lectures that cover the broad ambit of human knowledge. That is the arts, the humanities, the social sciences, engineering. We are particularly pleased always when we get a chance to combine two topics that might first seem at odds, like in this talk, art and mathematics. Now, as a scholar in my scholarly life, I know that convergences and coincidences often happen unexpectedly. And recently, that is, as I was actually thinking about this talk, I stumbled upon an article by an art historian, a very well-known one, Gulru Necipolu, which demonstrated that a work of the 10th century geometer, Abul Wafa al-Buzjani, was included in a Persian translation of a guidebook for artisans composed in the 14th century in Iran. So a theoretical work on geometry was included in a work intended for artisans. This manuscript serves as evidence of mathematics influencing art in a very clear and pointed way. But for me, personally, this article was really exciting, for I really knew the author of the mathematical treatise from the 10th century. You might find that weird, but I do really know him, I think. This Abul Wafa al-Buzjani was the patron of Abu Hayyan al-Tawhidi, one of the great literary scholars of the Islamic Arabic tradition and Islamic world. In Tawhidi's works, however, we meet Abul Wafa al-Buzjani as someone who rulers kind of employed in their courts to help them count their taxes. Kind of known as this kind of figure who did accounting, actually. I often thought of him as the sort of dour tax attorney or something. But I think it's profound and beautiful that his geometrical works, which may have been born of problems of assaying lands for taxation, because when you try and assess different shapes of lands, you need to use geometry to do so, went on to produce his own theoretical works and later to inspire artisan craftsmen some 200 years after his death. And it's with that hope of pleasure in abstract knowledge and its beauty that we bring this lecture and discussion to you tonight. And I just want to give a shout or a plug for also a talk that will take sort of theoretical knowledge in an implied context. On this Wednesday, we're having a talk here at the same time at 6 p.m. On how sustainability drives innovation and competition in business, where these teams, it's an actually really exciting event, where teams kind of show the way they are solving some complex real-world problems by often relying on the science that they learned in universities like this one. But on with the introduction, because it's my first and sincere pleasure tonight to introduce our own provost, Dr. Arlie Petters. Prior to joining us here in Abu Dhabi in 2020, Dr. Petters was the Benjamin Powell Distinguished Professor of Mathematics at Duke University and the former Dean of Academic Affairs for the Trinity College of Arts and Sciences. And he was also the Associate Vice Provost for Undergraduate Education at Duke. Petters' principal research interests include mathematical physics and scientific methods in business administration, with a focus on mathematical finance and entrepreneurship and innovation in STEM fields in developing nations. And I'd like to say, personally, it's one of the great pleasures of this job is to see folks that I meet in the day-to-day business of the university. And I get to see the things that they're most passionate about in their research and thinking. So with that, I give the floor to Provost Petters.
come up with me now. Yes, please. No, go ahead. How are you all? I want to thank you for joining us this evening. And I will say a few words of introduction about Jim, but I think perhaps what is important for us is the format. We want it to be conversational as much as is possible, and in many ways to have it resonate with aspects of your own intellectual journey. Well, I'll tell you, I've known Jim for quite some time. I was a graduate student at MIT. He was on the faculty at that time. In fact, his undergraduate, graduate degrees were at MIT, postdoc, if I remember, Caltech. Then from Caltech, you went back to MIT. What happened after Caltech?
Before Caltech, Harvard.
Ah, yes, I forgot. He was part of the Harvard Society of Fellows. And I will say that as a young, upcoming mathematical physicist at the time, having role models like Jim was extremely important to me. And if you look at Jim's CV, way over 100 pages, there is a lot of richness, a lot of human productivity in there. And his accolades span over many, many dimensions, not to mention, I believe, is it 10 now? Some 10 honorary degrees?
Yes.
I mean, this is just incredible. The Presidential Medal of Science, and it goes on and on. But I thought today, what we're going to do in some ways with what you're seeing now, Jim has like 3, if I may, set of slides. And the way I think of these sets, each one is like a photo album, but an intellectual photo album. And I would like to begin, Jim, with the early days, from when you were a student, where you were born, your parents, and then we're going to weave the story, right, as we go through this journey into the topic. So he's going to open up the first photo album, and we'll have a conversation around that. So Jim, tell us where you were born, a little bit of your heritage.
So, first of all, assalamu alaikum. And it's my very great pleasure to return to this campus. I was here in 2012 for about a week before the current provost, I would note, and had a wonderful time meeting some of the physicists here. So I am the grandson of a sugarcane farmer from Alabama. He was illiterate, could neither read nor write, but he could do arithmetic, which is sort of an unusual combination. His son, my dad, whose picture you see before you on the screen, that picture of Dad was taken in 1962, married my mother in 1943, and Mom is on the right-hand side. That picture of my mother is from 1942, by the way. That picture actually went with my father off to the Second World War. It sat in his breast pocket the entire 13 months he was in Europe. So my dad never finished high school. He desperately wanted his children to have the opportunity to get a degree. And so from my youngest ages, I can remember him saying, get your education, because they can't take that from you. And that's where it started. So this is the hospital I was born in. In 1950, African Americans could not go to general public hospitals. And so they built their own. And this is the place that I was born, the Lily White Hospital. If you know something about Southern culture in the United States, that name resonates in a very strange way.
That's right.
But by the time I was 4 years old, I was in St. John's, Newfoundland. Dad did 27 years in the U.S. Army, going in during the Second World War, lying about his age, going off to Europe. Stayed in, got out for about 2 years, got back in. I was born in 1950. And in 1953, I found myself in this place that you see here, St. John's, Newfoundland, up in the maritime provinces of Canada. Lived there for 3 years and acquired a liking for cold weather and the snow. My mother took me to see this movie once, a science fiction movie, a terrible movie. I actually have carried pictures of this thing in my head for now 70 years. And about 15 years ago, I started using those pictures to track down what the movie was, because I didn't know its name. Fortunately, we had the internet. I did maybe 5-10 years of searching, finally found this movie. And this is why I'm a scientist today. Because my mother took her then 4-year-old son to see a science fiction movie. And I'm told, well, I don't remember, that when Dad came home that day, I told him I want to grow up to be a scientist. In December, I passed my 74th birthday, so that dream actually came true. It's the only thing I've done as an adult. We came back from Canada in '56. This is the kind of airplane that we came back on. To the left side of that, you will see the passenger manifest. The actual passenger manifest that my sister found online about 5 years ago. Oh. Our names are listed there among the passengers. And that's me in 8th grade. I always tell people, when you see young pictures of me, look for the kid with the biggest ears, because that will be me. So I was in second grade. I was having trouble learning to read and trouble learning to write. And my father remembered that the 4-year-old version of me had said he wanted to grow up to be a scientist and astronaut. So he brought home some books on space travel. I was reading very quickly after that. So the role that parents play in providing a foundation for a young person is indescribable. Here's the whole family. We went from Canada to Fort Bliss in El Paso, Texas. So from ice to fire. But remember, I told you I had acquired a taste for cold weather, and therefore going to fire wasn't such a great thing for
Canada,
me.
yeah.
Here's my 4th grade picture. There were 30 of us. And I like to tell people it's easy to find me there, not by the ears, but because I'm the only one with a good tan. My mom died when I was 11. And that was the genesis of many things. I grew up instantly, losing mother. Life to me was never a mystery after that. I knew what the end of the story would be. And as a consequence, I've tried to live my life in a very purposeful way, in a way that after I'm gone, people will say, this is someone who made a contribution, not just to his family, not just to his nation, but to the entire world. As Arlie knows, I've been traveling the world for 30 years, trying to get people to understand the power that these things we carry between our ears have in order to shape our lives in more beneficial fashion. I spent Orlando as a teenager. These are my teachers from high school. Miss Thelma Dudley, the lady who taught me how to use the King's English. Miss Edna Williams, my first drill instructor in logic. Mr. Freeman Sanders, my Algebra 2 teacher. There's that word algebra. It shows up in 10th grade in my life. Mr. Reuben Patrick, who taught me to say things like parlez-vous en français? So, très un peu. I still speak a little bit of French. And Mr. Freeman Coney, who was my physics teacher. So as a 16-year-old, I understood the ideas of Albert Einstein because this gentleman brought these ideas into my life. Graduated as the, in English you would say best boy of my graduating class. In America we call it valedictorian. So I was a valedictorian of my high school. And at 14 I had started dreaming about going to this place, Massachusetts Institute of Technology. I was 14 years old, and I understood there was this college that allowed me to answer Dad's question about what college would you go to. I finally had an answer. It would be MIT if I had my way. I have to tell you, when I was 18 and finishing high school, my father had to force me to apply. You see,
tell us the...
Sure. So discrimination in my country is a perennial and proverbial issue. And all the time that I had been before Mother's death, I had been in, as you saw that picture, one of maybe 1 or 2 African Americans in the community in which I lived. But after Mother's death, we and my father remarried. We lived in Orlando in an all-black community. And it was the first time when I was confronted with the notion that as a person of the African diaspora, I couldn't possibly have the intellectual capacity to become a scientist. Now, this is a pernicious effect that you can see in many, many lives, in many, many places, and in many different circumstances. For example, the oppression of women and putting limits on what women can do. And so by the time I had finished 12th grade, I had bought into those ideas. And even though at 14, having identified this university as a place I wanted to go, by the time I was 18, I knew I could not be admitted. So my father, remember I told you, Army, 27 years, my other father said, "You will apply." And I said, "Yes, sir." And I applied. I didn't think I was going to get in. But one day I came home. He was sitting on the front porch. My father was never home before I got home from school. He had this huge smile on his face. And the instant I saw that smile, I knew I had been admitted to MIT. I ran to him, just like in the movies, and got this man hug. Because, we don't hug like women. We have this man hug thing working. That was the instant I knew that my dream that had started at 4 years old could still be sustained.
Yes.
These are some of my professors at MIT. Shirley Jackson, who's quite famous. She's an African-American woman. She was the head of the Nuclear Regulatory Commission, head of Rensselaer Polytechnic. In some sense, she is the mother figure for all of us African-Americans who majored in physics at MIT. These other folks, Vera Kistakowski was my recitation teacher in 801.
801? Okay.
801, that's what you call physics at MIT. You don't say
MIT
physics.
vernacular.
That's the vernacular, 801. He was my recitation teacher. Carl Engard was my undergraduate bachelor's thesis. It was on acoustics. And Professor James Young was my PhD advisor. Margaret McVicker is someone who taught me to respect experimentalists. There's me in that crazy hat. I was a crazy kid, even up in my early 20s, always looking to have fun and what have you. And the gentleman pointing at me is Brian Schwartz. We were talking to a group of students. And Brian is the person who first opened my mind to the idea of being a skilled teacher. One day I had given a lecture. He was standing at the door outside of the room. I didn't know it. When I came out, he said, "You look like you really want to be a good teacher." Notice that want. Right? He said, "If that's the case, I can help you." And so that's where the development of my teaching skills started, with that gentleman. This is me getting my PhD. Do I look bored? I was. You see, when I got my bachelor's degrees in math and physics, my parents did not come to the graduation. And from my perspective, graduation ceremonies are actually for the people who put the young folks there. It's not, the young people think it's all about them. But I never thought that. I thought it was about the people who put you on that stage. And since when I got my 2 bachelor's degrees, neither of my father nor my stepmother was there, I didn't go to graduation. I didn't see a point. But when I got my PhD, my dad made it a point to be there because I'm the first member of our family ever to go to college. And so he could see his dream of a member of our family getting a college degree, not stopping at the bachelor's degree level, but going all the way to the doctor's degree. So I'm bored there because I don't want to be there. That's why that look is on my face. I literally didn't want to be there, but Dad was in the audience, and I was not going to disappoint him. Went off to Harvard after that, and then to Caltech. I like to tell people I had the perfect circle afro in those days. And that's when I met these 2 gentlemen. The one on the left is Murray Gell-Mann, a very famous Nobel laureate in physics. The one in the middle is the person who invented this thing called string theory that some of you may have heard about in popular media, like the TV show The Big Bang Theory. That's string theory. This is the guy on the right who actually invented that mathematics. And I met this guy, Richard Feynman. He was the other leader of the research group I was in. So now you know something about my biological heritage and ancestry, but also about my intellectual ancestry. I was extraordinarily privileged to have these gentlemen and ladies see something in me that would allow that 4-year-old child's dream to become a reality. And then there's this gentleman, Abdus Salam. You see, in 1977, I was invited to the International Center of Theoretical Physics in Trieste because Abdus was interested in the mathematics that was surrounding a subject called supersymmetry, and we're going to get to that later. When I was a graduate student at MIT trying to figure out how to write a thesis, this is the topic that I chose for my thesis. And it's rather odd because you see, no one else at MIT knew anything about this topic, but I was convinced it was going to be very important. And so I had written some research papers, and Abdus was one of the people who had read one of those research papers, a community of us young researchers. And so we were invited to make a presentation in an auditorium not as fancy as this, but in an auditorium at ICTP, which is its main lecture venue. And he was sitting about where this gentleman is right here. And I'm up on the stage, and I'm thinking, oh my God, that's the guy with the Nobel Prize. He's the first Islamic scientist to get a Nobel Prize in physics. And I'm lecturing in front of him. And I don't fall flat on my face, step number one. And at the end of the lecture, he comes up and says, he invites me to come to his office to have tea. His office is in the second story of the International Center for Theoretical Physics, has a wonderful view of the Adriatic. And I walk in, I sit down, I'm nervous, because I don't know what he wants, actually. And the first thing he says to me is, you know, I didn't know you were a black man. This stuns me. So I'm a terrible jokester, as people who know me. But on this occasion, I resisted telling a joke. The joke would have been, I don't write mathematics and Ebonics. And you have to be an American to know what that means. But the second thing he said to me actually is part of what got me here tonight. And I'm not giving a recitation of what he said. I'm telling you a summary of what he was expressing to me. What he said was, he was convinced when a sufficient number of people of the African diaspora began to do physics, something like jazz would appear in the discipline. Now, when he said this, I had no idea what he was talking about. But because he had a Nobel Prize and I didn't, I said, yes, sir. Sounds reasonable to me. It took me about a decade to figure out what he meant by that statement, and we'll come back to that. So he created the International Center for Theoretical Physics. I spent about 5 consecutive summers there. It's near Venice, for those of you who may have spent some time in Italy. These are 2 different views. This is the center here, and this is the residence hall, where during my honeymoon, I brought my wife. We spent about 2 months there. This is the only picture in existence where both I and Abdus are in the photograph. There were other pictures, but I never acquired them. I was never someone to have a whole bunch of pictures taken. But this one was a conference. This is in 1988, so I got my PhD in 77, so this is 11 years later. It's about 10 years after I first met Abdus, and he created this conference where he called together scientists of the African diaspora from the mother continent, together with those of us who were part of the diaspora around the world, because he thought it was very interesting to foster the growth of a global community from this particular culture that he thought would generate the jazz in physics. So this is his effort to do that. By the way, some of you may have heard this expression, the jazz of physics.
Yes.
Well, you want to say something about that?
Well, you may remember Stefan Alexander came and did, the saxophonist and particle physicist, did a session on the jazz of the cosmos. And he picked up on the jazz of physics in that talk. And so, but yes, when we get to strings and the vibrations and all these lovely topics.
So there's Abdus, and there's me. I'm misbehaving in this picture. That's usually what I'm doing, if you catch me in my natural state. So Abdus and I had a 5-year-long, very intensive relationship. And part of it's actually captured in this article, which I found about 10 years ago. I don't know how the author got access to some of our communications, but if you read this, you'll see some things, at least one section about conversation that I had with Abdus. Abdus started a process in my mind of thinking about science and its development and mathematics and its development outside of the context of Western civilization. And this was a very important part of my education because I had been educated in the United States, undergraduate, graduated at MIT, first postdoc at Harvard, second postdoc at Caltech, first faculty position back at MIT. There's not a lot of diversity in that demographic background. And so part of why I now look back on my 5 years of visits to ICTP is because I now understand, at least I think I understand, why he extended those visits. Because I didn't have grant support. The Institute supported my visits there, and he was the cause of that support. And it puzzled me at the time. But I think the message was twofold. One, a very personal message for me to understand that mathematics and the universe in which we live does not have a bar against ethnic groups, does not have a bar against gender groups. It is our universe, and it's all of our universe. And I think that's the thing he wanted me to understand at a very primal and organic level. And because that's what I came away from the experience with. So that's the end of that part of the talk.
Well, Jim, I'll say that this first part with that personal journey, taking us through the U.S. and you meeting with Abdus, I was curious about a couple other elements before we go to the next album. Were you exposed at all to anything of the Islamic thought around art and its mathematics before you met Abdus?
No. Abdus was a portal for me, a portal into Islamic culture, a portal into Islam, and a portal into thinking about global culture and science and mathematics. So I wasn't. So he was also doing that without me understanding it.
Yes, and another thing, when we look at your photo from the PhD, one knows that as you go through these sociological elements, as you develop your career, there's a kind of resilience that it takes as you navigate through some of the emotional states that come with that. I didn't really want to be here. We all know that doing mathematics and physics is a tremendous amount of time and effort. And at times, inspiration comes from folks like him. Were there other mentors? I'll give you an example. When you showed the picture with the faculty that inspired you, Shirley Jackson, for example, was the person that interviewed me when I got my Bell Labs fellowship. That's right. So it's a very small world in many ways. And you also inspired me when I was at MIT. And in fact, I remember in my graduate school days studying out of your Superspace book. So all these things I feel helped me not feel isolated. It helped me feel a sense of intellectual belonging in many dimensions. So, but before we go deeper into the scientific part, were there other people that helped give you this resilience or continue to give you that push forward on those discouraging days?
Sure. Well, first of all, when I was in my late 20s, early 30s, I started to hear about this concept of mentors. And I didn't understand it, quite frankly. Why did people need mentors? But eventually I figured out the reason I didn't understand it is because I had so many that I hadn't known what to call them. My father was my first mentor, quite frankly. My dad, at age 17, lied about his age to get into the U.S. Army, to get away from the racial terrorism that was evident and manifest in Alabama in the 1920s when he was a child being raised there. And the fact that he lied about his age, and his mother, by the way, signed a document saying that that was his age, was an expression of his desire to build a better life for himself. He used to tell the story that when he was 12 years old, one day he told his father, Joseph, that, well, my grandfather, Joseph, as I said, was a sugarcane farmer, couldn't read or write, but could do arithmetic. And Joseph actually owned the property. He was not a sharecropper, which is very common in the African American story in the United States, the sharecropping families. And my grandfather had wanted to leave this land to his son. And my dad said, no, he wasn't going to be a farmer at 12 years old. Now, I don't know how a 12-year-old child comes to that kind of awareness of themselves and possibilities in their life, but he did. He spent 27 years in the U.S. Army. He became one of the first, in the U.S. Army, the highest enlisted rank is what's called a sergeant major. My dad was among the first 50 or so African-American sergeant majors in the history of the U.S. Army. When my mother died at 11, my dad raised his 4 children by himself while serving as an active duty soldier at Fort Bliss, Texas, and Fort Sam Houston Fort Bliss in El Paso, and Fort Sam Houston in San Antonio. And when I became a father decades later, I asked myself, how in the world did he do that? At my mother's funeral, I have memories of soldiers standing at attention around the edge of the church with pennants and flags. And that was because my father had so impressed the commanding general at Fort Bliss with his service and his dedication to being a great trainer of young men while having a family whose mother was dying from cancer. And therefore the father had to serve both capacities. This general knew this, and he was so impressed he sent his personal color guard to my mother's funeral. So Dad was the first mentor, which I didn't realize until I was in my 40s or 50s. There were many other people. When we were in San Antonio, I had a Caucasian American teacher by the name of Miss Canto. And this is after Mother's died and before my father has remarried. And Miss Canto saw something in me. And as a consequence, she invited me to go to her son's, who was in college, basketball game. So that human touch, people reaching out to you, leaves an amazing impression on a life. And I have just so many stories like this that I could tell about people who, as I look back, I don't know what they saw and why they did these things, but they did. Mr. Coney, my physics teacher in 11th grade, I was the only 11th grade student in his class of 12th graders, saw something in me and poured his love of physics into me. And so by the time I left his class, I knew it was not all of science I wanted to do, it was physics I wanted to do. And like I said, there are at least 100 people I could tell stories about like this.
Yeah, well, thank you for that. And as we transition now into the deeper scientific elements of your journey, I'll say in many ways this echoes what NYU Abu Dhabi is about. I look across the room, yeah? The diversity of humanity right before us now, each of us with our own journey, each of us going through our own sociology, each of us going through our own experiences, and that inner, I say, voice that you begin to engage with as you take on all these different elements of what you're hoping to do with your life. So we really love the multitude of pathways that the university offers. And so having highly distinguished scientists like yourselves come and humanize your journey is something that's extremely important. So yeah, tell us about this other part of your journey.
So, as I said, one of the people who's most been influential in my life, Abdus Salam. Abdus has been influential on a global scale. He has done something that, as long as our species is rational and depends on science and technology, his name is going to be there. To me, this is the greatest achievement of a life, to have left a legacy that is so powerful that millennia, just as we talk about al-Khwarizmi, right? Someone millennia ago has impacted our lives today. He is such a person. And to me, this is the highest level of achievement for a person. But this legacy I'm now about to describe is part of his scientific legacy. So we're going to take a Science 101 class here. Everyone knows that the universe is made of atoms. And this is my 54th consecutive year teaching. And in the fall, I was teaching a class called the Manhattan Project, which is about exactly what it sounds like, the development of atomic bombs. And I always like to ask students, how big is an atom? And so, I'm going to give you a pop quiz. How big is an atom? Now, this is a question that everyone's heard of atoms and atomic energy. It's a word you can't get away from. But how big is one of these things? And so there's a story that I was inspired to develop by my first physics class at MIT. It's called Powers of 10, which you may remember.
Yes,
but
I know.
Let me tell you the story. Imagine I had a meter stick, something about this long. I cut it into 10 equal pieces, throw away 9, keep 1. I go from something this big to about something like that. I do this a process again. I go to something about the width of my fingernail. How many times do I have to do this process to get to an atom? This is a question I put to my students whenever I teach this class. And some students say 1,000,000 times, 1,000 times. Does anyone in this audience know the answer to this question, other than the physicists? Because I know that they're salted around in this audience. I saw a couple of them. So you're not allowed to answer. Anybody else know the answer? Say again? It is not a big number. That's exactly right. It's 10. You do this process 10 times, and you go from our world to the world of the atom. This is a story that's very easy to remember once you've heard it. So the next time a professor gives you a pop quiz on how big is an atom, you'll be able to answer it. So there's a world even smaller than atoms. There are these things we call quarks, which are little things that sit inside of protons and neutrons. And protons and neutrons are in atoms. How big are protons and neutrons? And again, physicists are not allowed to answer. Almost. We normally say 15. We normally say 15. I know. But it's normally we take the number to 15. There's 17 for large, basically for large nuclei. And so this story I told you about powers of 10 is something that tells us how to get out. By the way, the first person to know how large an atom is someone you've heard about. His name is Albert Einstein. People don't talk about this, but among his 1905 works, he wrote something on what's called Brownian motion. He did some mathematics, and in order to get the mathematics to agree with the observations, you have to put in a number for the size of the atom. And he's the first person to know that an atom is 10 powers away from where we live. So the chart I'm showing you is a chart about things at the size B that is smaller than a proton or neutron. That's what these things are. And we know about these things from observations. You've probably heard of the Large Hadron Collider in Geneva. This is what they're experimenting on, are these things that are smaller than atoms, that are smaller than the nucleus of the atom. And there are lots of things we have found there. Well, not such a huge number, but more than you might imagine. And they're all listed on this table. So understanding how that small world works, that's part of Optus's legacy. There's a piece of mathematics connected to this chart called the Standard Model. And a large part of the Standard Model describes what's called spontaneous symmetry breaking And spontaneous symmetry breaking is why Abdus won a Nobel Prize. So his legacy, as I said, is as long as humans are going to be technologically knowledgeable, his name will be there for us. There's this thing called the Higgs boson. Now, let me do this again in case you weren't watching. I'll slip back and forth. There's this thing called the Higgs boson, which is directly related to his contribution to understanding this world of very tiny objects. Then in this world, there are only four forces. There's the gravitational force, just like for us, we sit comfortably in chairs. There's the electromagnetic force, like charges repel, we learned that in school. But there are two other forces that are not so widely known. Both of these other forces are nuclear forces. One of them is called the weak nuclear force, and the simplest way I can tell you about that is if I could hold a neutron in my hand here, outside of an atom, after about a minute and a half or so, that neutron would turn into a proton. It would turn into a proton, an electron, and a particle called an antineutron. It is the weak nuclear force that's responsible for that transition. It's called beta decay, by the way, by the nuclear physicists. We all look up at the sun every day. It is the life giver to our planet. It is not quite the exclusive source of energy for life, but almost, except for thermophiles that live at the bottom of the ocean and derive their energy sources from geothermal energy. But all of us on the surface, that's the source of our life. The physics of where that comes from is from this thing called the strong nuclear force. And so those are the forces that these tiny objects feel. But when we look at the mathematics of trying to describe all of this, you'll see I put an X on the gravity. That's because we don't really know how to consistently describe that in the presence of quantum mechanics. Here's another view of all those particles, different from that one I showed you. The other one I showed you, by the way, is widely known. In fact, that chart is made by the US Department of Energy. You can find it in high schools often. This is a chart you won't find, because this is a chart I made. And the reason I made this chart is to show something that is not obvious in these other representations. Of those particles that we saw in the other charts, they only occur in here and here. Now, the things that are here have a very special name called fermions. It means basically that no two of them can occupy the same place at the same time. The things in this column, which include the particle of light, many of them can occupy the same place at the same time. That's what bosons and fermions mean technically. On the other hand, when we went vertical, up here we're talking about things that are the carriers of the force, whereas on the lowest level, we're talking about things that feel the forces. And if you look at the standard model, as I've just shown you, you can classify them like this. And now, earlier today, I asked Arlie a question. Can you ask the audience this question?
Do you think there's something missing here? Is there something odd about the table? Yeah.
I think I see one person indicating.
Yes.
Do you want to speak,
Gonna
sir?
go for it? Who said it's not as many partitions, yeah?
So I like to say, does this look balanced to you? No. Because it turns out that we humans are exquisitely sensitive to symmetries. There are some studies that have claimed to show that what we call a beautiful face has got to be very symmetrical. So this is not symmetrical, and therefore, at some intuitive level, it offends us as a clear picture of how reality should be.
And that's your art.
And that's the art. But it's also Abdus's, because you see, what Abdus suggested is that it ought to look like this.
Much more balanced.
Much more balanced, and the only way you get this balance is by adding more things that were in the previous picture. This left-right balance that you see is called supersymmetry. It's a symmetry, but it's beyond other symmetries, so they call it supersymmetry. Abdus Salam in 1972, working with a physicist named John Strathdee, wrote some of the first mathematical descriptions of this kind of a universe. In 1972, I was an undergraduate at MIT. So that by 1973 and 74, when I was in graduate school, this is when I first read Abdus's writings, was on this subject. So this is what our universe looks like from all of our present-day experiments. But because we like symmetries, and by the way, symmetries have been driving physics since the time of Isaac Newton. Steven Weinberg, another Nobel laureate, once said that what Newton did was to unify the celestial with the terrestrial. Namely, that if you understand gravity on the Earth, you can understand how the gravity affects planets. That's the unification. That, by the way, is also the notion of a symmetry. That something in one place is true as it is someplace else. That's a symmetry. So, part of what Abdus gave us, Abdus's work builds on work that came out of the 1860s or so. Maxwell, a physicist, told us how light works. We know that light is actually a combination of electricity and magnetism. And these animations, by the way, that I'm showing are things that I had created in the early 2000s. I did a series for a company called The Teaching Company. They like to talk to the public about science. And I did a series called Superstring Theory, the DNA of Reality. And the way that I did it was by having a library of the pictures I carry around in here turned into computer graphics so that I can show them to people like yourselves as I give talks. And so this is what light looks like in terms of mathematics from the time of Maxwell. You might ask about, well, what does an actual photon look like? Well, in mathematics, since the time of Maxwell, we've actually understood that, but only in the last year has someone actually gotten an image of a photon. It was reported in a number of major scientific journals, the first human image of an actual photon, even though people like me have been seeing it, like I said, in math for centuries. I'm going to show it to you. This is what a photon looks like. And this will loop around and we'll start over. So the idea is, imagine a light particle is coming to us like this, and then we take a path through the light particle and go out the other side and look back at it. That's what you're watching. So now we're about to fly through it. Boom, we just went through it. And now, because we can't keep up with it, it's racing away. All right? Let me see if I can stop this at exactly the right instant. When you're right in the middle of the photon, what you see is a bunch of rings and some starfish. The actual picture of an experiment that was done last year in England using quantum mechanics has just been published, and what they found was a ring-shaped object with starfish sticking out. That's the power of mathematics. You see, mathematics is not just what you learn to write strange symbols on pieces of paper. For people like me, it's a sensory perception organ. It allows us to see parts of nature that other people are not able to see. And then when we go, the thing that distinguishes physics, theoretical physics, from other systems of human belief is when we say something, we then go and ask nature, did we get it right? And that's what the experiments are all about. That's why physicists are always talking about doing experiments over and over and over again. Because what we're doing is asking the questions, how correct are we in what we believe about the structures that occur in nature? And so I was very happy when this past year, when this actual picture of a photon came out. This was made, this cartoon was made in 204, 206. So that's part of what we do, and that's part of what Abdus thought about. But Abdus also had a high regard for art. My wife has a little glass goblet that he gave, that lives in our home, that he gave her while we were there on our honeymoon. Because he was very involved with the notion of symmetry and art. So this balance stuff that I told you about, that's closer to his aesthetic. And this is me when I became a professor at Maryland. The stuff behind me is, again, some weird piece of mathematics that is easier for me to show you this than to show you the actual mathematical formulas. This is something called a heterotic string. And now we're going to go to gravity. Remember that big X that we had up in the upper corner? The part where we humans don't know so much about? We're going to try to get into that region. Now, Einstein, because this guy pops up in lots of places, was obviously one of the greatest physicists, but he has also given us the deepest understanding about how gravity works. And he does it with equations. These are his equations over here. I try to minimize the math, so like I said, don't bring out the holy symbols and start to get nervous. It's not going to hurt you. But these equations for people like Einstein and for me, they're like looking at a score for a great symphony. You know, if you look at the score, there are a bunch of bars and symbols, and it looks like a mess. But you're not afraid of that because you know that if someone plays it, you might hear something you like. But that's what this stuff is like for us. It's that this math, which most people find unapproachable, is another language. It's like a musical score, and some of us can actually hear this score. And that's why we love it so much. So Einstein's equations tell us that space is actually acts like a flexing surface, and that when you put a planet on it, it bends the surface, and that bending is gravity itself. That's what Einstein teaches us. And so this little cartoon I had created, we see the Earth circling the bend that the sun causes, and that's why the Earth stays in its circular orbit. But Einstein also made a prediction that gravity can act like a wave. Remember we saw those particles, the wave property of light? Einstein's equations predict that gravity can behave like a wave. This prediction comes from it starts in 1915 with his theory of general relativity, and it comes fully into fore in the middle 20s. That gravity can behave like a wave. Now, we've never seen gravity behave like a wave until 2014. In 2014, these three gentlemen, Barry Barish, Kip Thorne, and Ray Weiss, finally had their dream come true. Because you see, their dream was to measure and observe the wave-like behavior of gravity. And they are the prime creators of a laboratory called the Laser Interferometry Gravitational Wave Observatory. And I've actually known Ray since I was a graduate student at MIT. Kip Thorne, you saw that perfect circle afro when I was Kip Thorne has told me he remembers me with that on my head, which shocked me. I didn't think he would. And Barry, I've only met much later in life. And so these gentlemen built a facility that is at the time they observed gravities, was located in 3 different places. 2 places in the US and on the Italian-French border. And that's what these little dots are, they're laboratories. What their laboratories measured was, if you look at this cartoon, these balls that you see going around represent neutron stars. They're extraordinarily massive objects. And the point is, when you have massive objects going around each other like this, they generate the waves of gravity. And so what Thorne and company did was build a device to measure these waves of gravity. And in 2014, the first such measurements were made. And once again, Uncle Albert gets confirmed in his ideas. His scores still hold as to the rules for how the universe worked. But we know mathematically that his rules cannot rule down where those tiny particles are that we talked about earlier, where the rules of quantum theory work. All of our atomic energy, unfortunately our nuclear bombs, all of that stuff tells us there's a whole different set of mathematical rules down there for these small objects. And when we try to apply those rules to gravity, you get nonsense. And so that's one of the great unknowns in human scientific understanding is how do you get to understand what's in that upper quadrant that I had the X in? And that's what I've spent my life, and there are a lot of us, my generation, trying to edge into that domain. And from my point of view, boosted there by Abdus, because he's the one who started supersymmetry, and all of my scientific work is about supersymmetry.
And tell us what you were looking at, Jim, just before.
Here.
Yeah,
okay.
that animation.
Sure.
Yes.
So what I tried to do with this animation is give you a sense of what quantum physics says about our universe. Imagine if I take if I build a box, let's say that, take a box and build it here, and I pump all the air out of it. Is there something there left? Most people would say no. And even Isaac Newton would tell you no. But due to Bohr and Schrödinger and Dirac and Fermi, we know that's not right. We know even if you remove every bit of matter that you can from some volume of space and just even make sure light's not there, there is still something there. We call it the quantum vacuum. And again, we know about this because of the experiments that we have done on these tiny particles. That's what I mean by saying the laws are different. And so what we're watching here is an animation I tried to create for people to understand that when you say that, saying that there's nothing in a piece of space is like saying, if I look at a lake on a calm day, the water will be perfectly still. That's sort of like nothing. But if there's some wind blowing, you're going to see waves on that lake surface, and that's what the quantum vacuum looks like. And we don't know how to mathematically describe gravity in the presence of such a structure. That's what the quest for quantum gravity is all about. It's why in 1980, Stephen Hawking invited me and about 30 other young people to come and talk to him about our mathematical work on supergravity. What's supergravity? It's the idea of that balance together with Einstein's equations. So we were putting them together, packaging them all together. And that's why Abdus had me come to ICTP, because of my work on supergravity. So that's what the drawing is. You want to stop here or change gears? What do you want to do?
Great. So, I mean, I really enjoyed this intellectual journey so far, and I sense with this now the connection with art and the way certain graphical representation encode profound meaning in physics. So maybe take us into this part here, and I will continue to keep track of time.
Okay, very good.
Right?
I'm worried about the
and
time.
that word there under symbols.
It's called a dinkra.
Yes.
Yeah. So let me keep going. Once more, we descend to the underworld of mathematics.
Yes.
So here's some equations. And these equations, by the way, are the type of equation Abdus invented. Supersymmetry equations. They have that left-right balance. So there are a lot of things about this mathematics since it's relatively new. Well, 50 years, 60 years. But from the perspective of the universe, that's the blink of an eye. There are a lot of things about this mathematics we don't know to this very day. And so in 2004, working with another physicist named Michael Fox, we learned something very interesting about the equations that Abdus introduced us to. Namely, they could be represented as pictures. That is, these images that I show you contain data that's the same data in the equations I showed you a few seconds earlier. Now, Michael and I were the first people to figure this out, that the math equations could be turned into what mathematicians technically call graphs. There's a whole part of mathematics called graph theory that's on pictures. There's certain axioms you have to satisfy, but when you satisfy them, these pictures are mathematics. And so we stumbled into one of these sets of things, trying to understand properties of the equations. Now these objects, I'm going to go, come in different shapes. I'm just going to run through some of them. But one of the most bizarre features I don't know how many computer science majors we might have in the audience, but in computer science, there's a notion of error correcting codes. It turns out that these equations contain error correcting codes. So as a consequence of this, now we don't know if that left-right balance, we haven't observed that in nature, so we can't claim we know this is how the universe works. But if we ever as a species confirm that balance, then the things I'm telling you now will go from speculation to being scientifically demonstrated. And so what I'm about to tell you is that this picture here, which is one of our graphs, where we show the computer codes on top of the nodes, is the first example of a law of physics where error correcting codes are built into the law of physics. And that's where my dream is. To me, this is the most important thing I have ever discovered in my research about our universe, is that some of its laws may involve computer codes, error correcting codes. So when Michael and I first...
I couldn't help but make the remark, maybe it's a matrix indeed.
A lot of people trouble me with that idea, that maybe we all live in the matrix. Again, I don't know how many of you have seen the movies The Matrix, but a lot of people have said that the research that Michael and I recovered must imply that all of us are in the matrix. Mm-hmm. I don't believe that for a moment, but a lot of people have said that.
Yes.
I know. And that's why the title of my talk was Superstring Theory, the DNA of Reality. So let me just take you through some of the artwork. Here's some simple figures. But as you get more and more complicated equations, the pictures get more interesting. And I have to tell you, those to me are pretty nice pictures. We did not do anything to tell the computer to make pretty pictures. What we did is we took masses of equations, we applied the same technology that went from those 4 simple equations to that first simple picture. We applied exactly the same technology, and part of those technologies is developing computer algorithms from our hero, Al-Khwarizmi.
Yeah. I don't know how many people in the audience got that, maybe 30 seconds on that connection?
Yes. So if you're writing computer programs, you have to master the art of writing the instructions for the computer in order for it to figure out whatever it is you want to do. These instructions are called algorithms. They are the instructions to the computer to execute a set of mathematical steps to get to this, get from a starting point to whatever you designate as the end point. And this process of writing these things was first described by Al-Khwarizmi. So we honor him by, to this day, calling this process algorithms. So we have found other objects that are less interesting visually, but much more interesting to us mathematically. So I just want to showcase those. And now back to the gravity thing. As I said, I was in Feynman's group. He's one of the quantum people out there. He would not be happy with this still surface that Newton says. He says it's got to be like this. You got to read your physics in the presence of the fluctuations, the vacuum fluctuations. And so here is the combination, but let me get to this guy. Most of you probably have never heard of this person. His name is Edward Witten. He is regarded as my generation's Albert Einstein. Now, most of you have heard of people like, name some popular physicists, Brian Greene,
yes.
Neil deGrasse Tyson, Brian Cox in the UK, Jim Khalili, right? Those are the names that people normally associate with science. Those people don't do science, they talk about science. This is the alpha guy doing science. His name is Edward Witten. I've known Ed since 1985, and let me tell you, I've never met another person that smart. This guy it's alien. I don't know any other way to describe it. But I'm not the only one who knows that Ed is smart. So does Brian Greene. Read what he said about Ed. That Ed's intellect is terrifying. So in '95, Ed tried to bundle the two parts up, gravity and the fluctuations. And he came up with a set of equations called M theory. And this is part of the beginning math of that stuff. But when Ed formulated these equations, since he's formulated them, very little progress has been made in understanding the structure. And so I, in the back of my mind, knowing how to go from equations to pictures, decided I'm going to apply what I know to Ed's construction. Oh, by the way, I should stop perhaps. Because you see, you know, physics is a very strange thing because it kind of seeps into parts of life. Like you all know the words atom and you all know quantum leap, right? These are words that you all have heard, but they all start in physics. And so this process of physics creeping out into the world, unfortunately, has begun with my research. This is a friend of mine named Mark Richards, who is a physicist at Imperial College in London. And in 2023, he was out in the streets, and there was a street vendor selling T-shirts, and Mark saw that T-shirt, but Mark knows the origin of that T-shirt. It's actually our figures where we take pieces of math and turn them into pictures. And so our stuff is slowly, perhaps, creeping out of the laboratory? Well, back to the physics. So in 2020, working with my two graduate students pictured here, Hazel Mock and Yangre Hugh, we actually solved in a way that no one else had previously done part of Witten's M theory equations. We basically were able to define the equivalent of what you might call a quantum ground state. And we did it not by looking at the equations. We studied the properties of the pictures that we turned the equations into, understand those patterns, and then use those patterns to give us back pieces of mathematics. So it's not that we're appreciative of the math turning into pictures. We are demanding that that the pictures back react with us and give us mathematical answers, and we are able to do that using computer programs. Mm-hmm. So let me. By the way, there's a problem with 4 billion yes or no's that we had to answer. And we did with the computer code. The figure that we use looks like this. It's not very interesting, but I like to tell people things like this. This is a picture my son created. I have a son who is a biologist, but he's really good with computers. He's about to get his PhD probably next year. He has a twin sister, by the way, who studies black holes. So we're kind of a STEM family. My wife is a medical doctor, by the way. So STEM is all over us. He also did this. Mm-hmm. Yes. So I think we should perhaps pivot from this point. Let me just, as we pivot, make some acknowledgments. All those animations I've shown you come from this video called, it's actually streaming now, called Superstring Theory, the DNA of Reality. And it used to be available on DVDs. And these are some of the folks who really were instrumental in me achieving what I've been able to achieve. And I have to give a special shout out to Ken Griggs, because all those computer animations that you saw were actually done by Ken. So we can leave this now.
Yeah, well, thank you so much. Let's give Jim a big round of applause.